Good morning again. First, I would like to answer any questions, so please use your microphones or chat within this lecture. Well, okay, no questions at the moment, so we will continue or return back to the problem on a bit higher level. We have been developing the Laplace equation, and to do that we have found that there is no free charge at the area. Just remember, we did it just here. So we said, okay, we have no free charge, so we have here 0. If there was some free charge, that would be the density of the charge on this side. So switching back, we can formulate the situation for an area containing also free charge. So we would have minus epsilon nabla phi is equivalent to free charge density for an area where a free charge exists. Now this is quite tricky. The free charge there must be somehow bound or sticked to the position, otherwise the electrostatic force would drag it out. But let's say we have some area where we have built a free charge which cannot move, and then this could be the situation, and the equation becomes Laplace phi as minus charge density divided by permittivity. So instead of 0, which would be the Laplace equation, we have the Poisson equation, which is like this. Now again, we can solve this equation by successive integration. I will do the first step, so integrating in one dimension this. So let's switch to one dimension only. Then it is the second derivative of phi against x, equivalent to the right side. So we get the first derivative. We should put down the ordinary derivative of phi. And what we get? Well, we should integrate this, which is minus rho 0 to epsilon. So minus free charge density divided by permittivity multiplied by x plus the constant c. Or we can integrate it once more. We should do it. Shall we obtain the equation for phi? So okay, phi is equivalent to, well, we first integrate this and obtain minus rho 0 over epsilon x squared divided by 2. That's the integral of x against x. Well, plus we get cx plus we get the constant k. So now we have a function that for 1D cases covers all possible distributions of potential, which is in a 1D case in the presence of the free charge. Just a remark, this free charge rho, this free charge density, might be a constant, but might be a function as well. At this moment, we will again get to more or less the same case. So we have two electrodes that are plumb parallel. One electrode, second electrode. This electrode is X equivalent to 0. This electrode is X equivalent to D. Now, this electrode is at potential phi equivalent to 0. This electrode is at a potential phi equivalent to V. So far this is completely identical with the last situation. But now we get a homogeneous free space charge density ρ0 here. And now let's get to the solution. We again have a general solution, as I said, and we will have to investigate it for the two boundary conditions, hoping to establish those two constants C and K. Let's start with the left boundary. So phi should be 0, x should be 0, substituting 0 here and 0 here. We will get 0 is 0 plus k. So the first constant is easily established, k equivalent to 0. Well, okay, let's go on to the other boundary. Substituting d for x and v for phi, we would get a bit more tricky equation, which is v is equivalent to minus charge density divided by permittivity, d squared divided by 2, plus c d, k is 0, so this is the equation. And we can solve it quite easily. Just we move this to the other side, we get v plus charge density divided by permittivity d squared divided by 2 is equivalent to c multiplied by d. Then we divide the whole equation by d and obtain a solution for the constant c, which would be c is equivalent to v plus and that's it. We have a general form of the solution. The form contains two constants. We have established both of them, one and the second, and we have therefore the general solution to the problem. Now let's investigate it a little bit. So first we can see that there is a quadratic function within it. And therefore, let's draw it. So first, let us draw the solution for a very small charge density. That is the last case of a Laplace equation. We had the potential ranging from 0 up to v as a linear function. And at that moment we also note that the electric field flux density has the same direction and is homogeneous. At any point has the same value. Now what if there is a small charge density? Well, okay, we had there, just remember, we had there the equation, and there is something like minus x squared So if we have the function minus x squared, the function as itself looks like that, minus x squared. Just with the top at x equivalent to 0. So if we combine those two functions, we would get something with a bit different shape. The beginning and the end are fixed by boundary conditions, but the curve would a little bit stretch and look like this. So this is the situation when we have some small charge density in between the electrodes. Now, the important point, the electric flux density, neither the electric field strength, would remain homogeneous. As you can see, the field strength is given by the slope of this curve, and the slope changes. So we have stronger field here and less strong field here. Well, let's go on. What if the charge inside the layer grows bigger and bigger? Well, then there is more of that parabol, and we get finally something like this. Again, both ends are fixed, but this situation is a bit different. We have some maximum potential inside the layer, and at this moment we can easily see that in this part we have this orientation of electric field strength and flux density, but in this part we have the opposite orientation. So at this moment we have a point when there is no flux density and no field strength at the middle, and we have two areas with opposite orientations of the flux density. Why this is happening? Well, in fact, in the first case, the main source of the electric field was the charge deposited at those two electrodes. But now there is a change. We have a charge that is in between those electrodes, which creates a field which points from the charge to the electrodes. And we have at the same time the charges at the electrodes, and the composition of those two fields gets us to this situation. And this situation is somehow similar to a situation of a p-n junction, where you have, due to the forces between p and n parts of the semiconductor, you have a cloud of charges, and this cloud of charges in fact causes the behavior of the p-n junction. Your questions? If there are no questions at the moment, we should proceed to another topic, which is boundary conditions at an interface between two dielectrics. Now, this is an important topic because it allows us to solve fields that are resident in complex bodies, like bodies that consist of several different parts, layers, of different materials. So now let us first put the important equations to the top of the paper. So we have electric flux density as a product of permittivity and electric field strength. So that's the first equation. Then, the other important point. Any vector could be decomposed into its constitutive components. If we have a boundary, we would have two parts of a vector, two important parts, components, that behave in a different manner. If we have a boundary, then there is the boundary, and you can have a part of the vector, which is called normal, that crosses the boundary. And there is a second part of the vector that goes parallel to the boundary and never crosses it. That's a tangential component. So a tangential and a normal component. We would be investigating separately tangential and normal components. Now, let's draw a simple interface between two dielectric materials. This is the interface. Anything higher than the interface has the index 1. Anything under the interface has the index 2. So there is, for example, permittivity of the upper part, epsilon 1, and the permittivity of the down part, which is epsilon 2. And as we want to talk boundary conditions, we inherently think that those two numbers are different. Then we have the tangential component of E, tangential 1, and the normal component of E normal 1, and the tangential component of D1 and the normal component of D1. And vice versa for the other part. Now we should investigate the conditions under which those two numbers should be related. I mean the numbers over and under the interface. Now there is first important point. We have one quantity which we call potential. And what would be important for a potential? Just imagine that we have at one point that the potentials over and under are equivalent. Should they be equivalent? Well, what would happen if they are not identical? Then it means that crossing the boundary from the very tiny layer over it to the very tiny layer under it, so in fact on a zero path, you would get from one potential to a different potential. But that means that there is a finite work carried out transporting a charge on an infinitely short path. As the work carried out by a force is a product of the path and the force, a finite work over an infinitely short path would mean an infinitely big force. In the case of electrical field, if there was a different potential over and under the interface, it must mean that there is an infinite electric field strength over the interface, which would then create a discharge and unify those two potentials anyway. So we know that potential is strictly constant when crossing the interface. or the potential over and under the interface must be at all cost identical. So we do not need to put in indices for the potential. There is only one potential on the interface on both sides. This is an important property of potential. Potential must be continuous, because discontinuing a potential would cause a discontinuity in force and energy. Okay, so we have established a rule for potential. On the interface, it must be continuous from both sides. We are done with potential. Let's go to electric field. Electric field strength, E. So let's first start with the tangential component. So we have tangential components here and here, just over and under the interface. Now we can use what we have told about the potential. Let's consider that we have a potential here, phi. Now, the electric field strength is, in fact, a derivative of the potential along the surface. And so it means that it tells us how fast the potential changes. Now, imagine that those two field strengths would be different. That would mean that I have some potential here, which changes faster here than here, or vice versa. So it must yield to a situation that after a certain path, you would get different values of potential over and under the interface. That is impossible. So we now know that the tangential components of electric field strength must be identical. So we have an important rule that says that E tangential 1 is E tangential 2. So the tangential components of electric field strength must be identical. If they were not identical, it would violate the condition for potential, which in fact would mean that there must be an infinite energy contained somewhere around the interface. So we have a second important rule: the tangential component is identical. Now, if this is the true, we can also tell something about flux densities over and under, that is d tangential 1 and d tangential 2, because both of them are given as a product of the tangential field strength, which is upstairs multiplied by the permittivity epsilon 1 and downstairs multiplied by the permittivity epsilon 2, according to this equation. So we have d tangential 1 is epsilon 1 E tangential. I do not put index here because it is referring to the same value. And the d tangential 2 is equivalent to epsilon 2 E tangential. So now what we may do, for example, is we may divide those two equations because they are non-zero, and we get d tangential 1 over d tangential 2 is epsilon 1 over epsilon 2. And at this moment we have obtained second boundary condition that binds the values of tangential components of electric flux density over and under the interface. So at the moment we have established the condition for potential and for tangential components of electric field strength and electric flux density. Are there any questions? Thirty more seconds for questions. Okay, so still no questions. We shall have to stick to normal components. And to do that, we will draw another picture. Let's say we have a thin sheet interface between two materials, again the same picture, and let's put there a cube. So we have there a cube which is half buried under the interface, half stretching over the interface. Then the cube is inserted in the way that the walls are perpendicular to the interface. Now, remember, this is something we have been investigating at the moment when we investigated the universe in which there was only one charge placed on a tiny sheet and the rest was empty. And at that moment we said, okay, there is no electric flux flowing through the walls. The only place through which the electric flux might flow out is through the bottom and cap of the cube. So, in fact, there are two important situations. First, what about the situation when there is no charge at the interface? Well, then we have the integral equation that says that the integral over the surface of a body which integrates flux density over the surface is the charge which is contained in the body. But we just define the charge to be zero. If it is a zero, we have no other way to satisfy this condition than to tell that the d normal 1 is equivalent to d normal 2. Now, this depends on the orientation. So we have d normal in this direction, and this direction is the d normal 2. So the d flows uninterrupted and unchanged through the interface. If this is the true, we could also establish an equation for the electric field strength, for the normal component. We would have E normal 1 as d normal 1 over epsilon 1 and E normal 2 as d normal 2 over epsilon 2. Again, as there is nothing against dividing those two equations, we would get E normal 1 over E normal 2 as epsilon 2 over epsilon 1. So we have now established a boundary condition for the case where there is no free charge at the boundary, and the boundary condition has two parts. We have the flux density, the normal part of the flux density, and we have the normal part of electric field strength. Now, it seems we are done. Unfortunately, this is not the case, and I would like you to remember it, because we have an important number of problems where we have charge at the boundary. At first sight, it seems strange. Charge should reside in some volume. So what about a charge sitting on a dielectric, this non-conductive, where the charge appeared, why it holds there? But anyway, you must have witnessed cases that are caused or create charge density on a surface of a dielectric. You must have witnessed it many, many times in your life. How that happens? Well, for example, what happens if I get two sheets of paper and start to move them? Well, in this manner, some electrons from one of the materials are caught by the other material, and there is created a static charge on the surface. So although we have two dielectrics, they are both now charged because the papers are of different nature. One is more ink, the other is inkless. So I have now created a static charge on the boundary of those two places. In fact, the first generators of electricity known by humankind were using static sources like this. You know, that was a foxtail and an ebonite stick. Even very powerful generators are still today created by an endless belt circulating around. It's called a Van de Graaff generator, and they are capable of producing millions of volts. We have a big Van de Graaff generator in our heavy current labs. It really creates millions of volts. Those sources are, for example, sometimes used for particle acceleration. So this is an important issue. It works. It also causes sheets to stick together. Electrostatic charge of opposite signs created by just moving two elements rolling over the other. There are created charges of opposite signs, and those tend to stick those two layers together. So this is also used, for example, for sticking papers to plotters. So electrostatic force, an electrostatic case where we have two dielectrics and there is a boundary between them which is charged, is important. Now let us investigate quite shortly in two ways what happens if there is a charge sitting on the boundary. Well, in fact, using the integral approach, we will get another equation which says, okay, we have the integral of d over the surface, but it is not zero, it is equivalent to the charge sitting inside. So let's say we have a homogeneous case and that the box is just 1 meter by 1 meter by 1 meter, for example, so then the charge would be equivalent to the charge density, and we would get that d2 minus d1 both are normal components, is equivalent to the charge inside, I would use the sigma as the charge density over the surface. So this is the charge sitting at the interface, and it causes those two values to be different. Okay, let's look on that from a different perspective. So we have a field without a charge. There is the same component of d normal upstairs and downstairs. It just goes through the interface unchanged. Now we add there one small positive charge. Well, the field of this charge is known. It will point out from the charge upstairs and downstairs. This is the flux density of this charge. Well, it should have equal lengths upstairs and downstairs, so something like this. Now, upstairs, the field is subtracted from the incoming one. Downstairs, the field is added to the original one. And therefore, if we have a number of those charges all over the plane, we know that the difference between those two ones must be the charge, which is again the same equation. The charge density is the difference between those values of normal flux density components. I would like